guess we'll start getting ready for our next speaker, and I've been practicing the name. So next we have Drgona, speaking about differentiable optimization as a lingua franca for scientific machine learning. Jan is a data scientist in the Physics and Computational Sciences Division at the Pacific Northwest National Laboratory. Before that, he was a postdoctoral researcher in the Mechanical Engineering Department at KU Leuven in Belgium, working on advanced constraint control methods for energy systems. He has a PhD in control theory from the Slovak University of Technology, Slovakia, and his current research falls at the intersection of model-based optimal control and differential programming methods. And I love his first slide, it's beautiful.
Thank you very much for a very warm introduction. And I would like to thank Shomik and Ethan for the invitation and for the opportunity and the privilege to be here in person. I am very grateful for this, and I'm super happy after 2 years of staying at the home, actually being at the first in-person event. This work, what I'm going to present, is not only my work, this is the work of our smaller and also like larger extended team. I'm highlighting only the closest collaborators here, namely Aaron Tuer, Shriyank Abhyankar, Ethan King, Stefan Dernbach, Difan Zhang, James Koch, Zhao Chen, and Drgona Vrabie, who are working as an interdisciplinary team at PNL. So my topic of the slide is differentiable optimization as lingua franca for scientific computing. This take is our own personal take from our team. How do we communicate between different scientists who have background in computer science, constraint optimization, control theory, dynamical systems, power systems, molecular dynamics? There are huge barriers when you are starting to, as a data scientist or as a computational scientist, discussing things with people from domain who are very deep in the domain. They have their own jargon, they have their own tools. How do we bridge this gap? So I don't want to impose anything on the domain or community. This is our take, what has been working on in our team, where we started with main motivation, how do we do simulations at scale? Because they are crucial factors for many areas in decision-making and scientific discovery. And the need is to improve the accuracy, but as well as scalability of traditional mechanistic models, as we have been hearing from wonderful talks before. And because we are at the National Lab, our job is not only to do the basic research, but also to do the tools development and scaling up very promising ideas like physics-informed neural networks. So our objective here is to develop domain-agnostic software tools and unifying algorithmic frameworks that could support both scientific computing and data science in one unifying framework. Our applications from high-level perspective are constraint optimization problems, modeling and control of dynamic systems described by ODEs, PDEs, differential algebraic equations that are ubiquitous in engineering and science. In our team in particular, we are interested in modeling and control of large power system networks, and going way deeper down, we want to also model molecular dynamic systems, and in between we have some building control and aerial vehicles problems that we are interested in. So our take from these type of problems is, how do we solve this? Everything is about optimization. Whether you deal with solving engineering problems using scientific computing tools, whether you are dealing with machine learning, you are doing some sort of optimization. You are finding your optima of your primary decision variables that lie at the saddle point of your loss functions that represent your problem in some way. Different communities have been developing different solvers, different solution methods, different frameworks to formulate the problems for solving their particular problems. My personal background is in control theory and constraint optimization, so I have very strong bias of like thinking from this framework. So I just want to do a quick quiz, so I adjust also my explanation, like who has background in constraint optimization or control theory? Okay, quite some few people. And who is more like on the side of data science? Okay, great. And who is more on just pure engineering, like mechanical engineering or material science? Okay, few. So like I can go and talk about constraint optimization and the principles in a rather quick way. If there are any questions, please feel free to stop me anytime. I can explain something is not clear. So in constraint optimization, we write our problem in this standard form, where we have nonlinear objective function, that is a function of a primary decision variables x, can be whatever, and you have inequality equality constraints. How we solve this? We formulate this in some algebraic formulation language like CVXPy or Pyomo in Python, Jump in Julia, or Realm in MATLAB. And this language parses this formulation in specific form that is required by a typical solver that depends on the problem formulation. When it is quadratic problem, then you solve some kind of interior point or active set methods. Commercial solvers like Guro, B, or Cplex will do the job. For more complex problems, you do interior point method like IPOpt for nonlinear optimization. When you are dealing, for God's sake, with mixed integer problems, you need to go branch and bounds, branch and cuts. There are some efficient solvers out there, but all have something in common. You need to have hard-coded all your objective functions and equations of inequality equality constraints. And for each new parameter, which can represent different initial conditions, different boundary conditions, let's say in optimal control problems, or different right-hand sides on your simple linear equalities, AX equals B. Well, you need to recompute this the same problem again. So that is what is called online optimization. And in real-time decision-making, this is very crucial. How do we compress this on limited computation hardware in limited time? So speed of solution is a decisive bottleneck on many real-time optimization solvers. What is happening under the hood? Many of these solvers reformulate the problem in so-called Lagrangian form, where you put your inequalities, equalities inside your objective, and you have these variables, lambda and sigma, that represent Lagrange multipliers. What is Lagrangian? It has beautiful representation in physics, Lagrangian mechanics. You take the gradients and it gets you direction towards your saddle points. And that's the same idea here. The Lagrangian of the constraint optimization problem represents this abstract energy landscape of your problem that can represent either pins, or it can represent optimal control problem, optimal design problem, network optimization problem, you name it. And you want to find the saddle points that are actually also essentially constraint optimization theory. They're called Karush-Kuntaker optimality conditions. They are necessary conditions where first one is stationarity. You are finding where the gradient is equal to 0 of this Lagrangian. And then you have other conditions like this primal feasibility. Constraints needs to hold dual feasibility. Lagrangian for inequality needs to be larger than 0. And you have also complementary slackness that is telling you that either Lagrange multiplier for inequality or inequality is 0. So like these are technical details, but that what is leveraged by these constraint optimization solvers from that domain for solving this real time again and again. There is also a domain what is called parametric programming that emerged from operational research in 60s, 70s, 80s, based on sensitivity analysis of constraint optimization problems. That is somewhat different. They ask the question, can we pre-compute parametric solutions to the distribution of constraint optimization problems without recomputing them again and again in real time? The answer is yes and no. We can do it in theory. We know how to formulate these problems where you have nonlinear objective, but now the objective is not only a function of primal decision variables x, but also your parameters theta. Again, they can represent varying initial conditions, boundary conditions, or just some parameters of your equality, inequality constraints. We assume that they belong in certain set that can be either given just simple box bounds, or it can be polytopic set, depends on your domain. The problem is that these solvers, parametric programming solvers, they don't scale. They don't scale at all because you have what is exponential blow up in complexity, because they are based on analytic solution of your Karush-Kuntaker conditions and exploration of different possible combination of active constraints. And these, what are active constraints? They are the constraints that are on the decision boundary, and they matter the most because that's where your optimal solutions lie. And there's a problem because the standard analytical solvers, they are doing brute force enumeration of all possible combinations. So you add more variable, add more constraints, and you forget about your problem. We can solve only toy problems with parametric programming. It's beautiful theory, beautiful idea, but utterly non-practical. I spent half of my PhD and scratching my head why on earth we want to study this. So that's when all this revolution of machine learning came in. Physics-informed neural networks, wonderful contribution by George and the others in the domain, like a huge community gathered around it. And then we start thinking, can we use machine learning and these ideas from physics-informed neural networks to help us to solve these constraint optimization problems, especially parametric programming ones, because they are very, very hard. People typically think of machine learning as standard, like offline optimization, black box, no constraints. I like to think about constraint optimization perspective. So where are the constraints hidden even in black box machine learning? Well, you have your machine learning model, F, which, okay, is function of X, but in this case, X are data points, not primal decision variables, and theta, which are trainable parameters of your machine learning model. You have simple linear model, you have polynomial model or neural network. What are these? These are equations. These are parametric equations that represent the first and only constraint in your black box machine learning model. The difference is that you are finding the parameters of these constraints that fit certain data. Well, can we use the same principle, finding the parameters of some parametric functions to fit the solutions of parametric constraint optimization problems? Well, definitely we cannot do it just by sampling. Well, we could, but you would need to solve a lot of optimization problems that is expensive. Can we do it in unsupervised way, like you would do it in pins? The answer is yes, if you leverage the tricks or ideas from Lagrangian optimization. How can we compute the sensitivities of the Lagrangians of parametric optimization problems using automatic differentiation to guide our gradients of machine learning model? That will no longer be black box. You will have these constraint optimization or physics-informed residuals in your loss functions, very the same formulation like in pins, that will be added into your problem formulation. Another direction is like just to impose some architectural constraints in your computational graph of your machine learning model. I want to talk about the both perspective. We call this internally differentiable parametric programming. The formulation of the problem is as follows. Again, you have a nonlinear objective with primal decision variables X. In this case, I'm using psi for parameters. I apologize for switching the variables. Now we have primal decision, primal constraints, equality, inequality. We have some machine learning model or some mapping of our parameters to these primal decision variables. Let's assume that's our best case on black box structure of the solution map. And we have some parameters that are sampled from a distribution of the scenarios. Well, what do? We reformulate this into this Lagrangian form. In the simplest way, we can use penalty methods by penalizing the residuals of your inequality equality constraints. And again, they can represent your differential equation, they can represent your algebraic equation, they can represent boundary conditions, they can represent adjacency matrices and the topology of your network you want to optimize. And now you can use gradient-based optimization by leveraging automatic differentiation. So again, very similar, and I would say almost identical to the pins, just using kind of pins idea in the constraint optimization domain rather than solving differential equations.
Good question.
Yes, please.
What is pi then? Pi is the neural network that is mapped.
Most typically is neural network. It can be any differentiable function. So.
And that is parameters for theta, and that's the only thing that you're optimizing.
Exactly, that's a good point. So in classical optimization, you are optimizing for primal decision variables X. In parametric programming, you are optimizing for the parameters of your parametric solution map that maps your samples, which are basically each sample represents a different optimization problem. Yeah, with the same structure. So we are leveraging the structure here. So our take from software development perspective was, okay, there are no tools out there which we can just grab and use, but there is tons of software in automatic differentiation. And that what fueled the boom of deep learning. Widely accessible, popular, user-friendly automatic differentiation tools like TensorFlow and PyTorch. We introduced Neuromancer internally first, and this is probably the first external presentation about this tool. Is basically acronym for neural modules with adaptive nonlinear constraints and efficient regularizations. Our objective is to provide this open source tool for differentiable programming to support a range of problems in constraint optimization, optimal control theory, and decision making. Our current applications include molecular dynamics, power system modeling, and control of buildings, and some underwater unmanned vehicles alike. So as I mentioned, our enabling methodology and theories are based on parametric programming that is based on sensitivity analysis, and automatic differentiation for computer science, which is the sensitivity analysis done right at scale and in automated way. We have first version of our tool available and GitHub open source. Feel free to check it out and come back with any questions. There are some examples and we are working on more. What we currently support is solution of linear, quadratic, nonlinear programs. General, like you just define your equalities, inequalities, and you pre-compute the parametric solution. We are also exploring some combinatorial optimization like mixed integer, but I will not talk about that because it's a very, very early stage. We want to support general pins because there's wonderful technology, classical neural network architectures, which we can impose ideas from constraint optimization, graph neural networks. Modeling of dynamical systems, of course, is a big deal using neural state space models, neural differential equations, very successful models, which we are supporting. And why we are doing it? Because we want to use them in optimal control. And there, what we are solving parametric optimal control problems through the method we developed, we call differentiable predictive control. So I want to quickly introduce the ideas and examples from differentiable constraint optimization. I'm on time, please. 5 minutes. I should speed up. Here is the API of the Neuromancer. We want to make it as clean and as user-friendly as possible. For people who are familiar with CVXPy or PyOmo, what you do, you develop the problem based on defining some symbolic variables, and then you build your constraint optimization problem through high-level algebraic language. We do this through operator overload. Everything is on the top of PyTorch, so we have the PyTorch automatic differentiation. We have access to the whole PyTorch ecosystem where you can just import any kind of PyTorch architecture. You put it in the wrapper. Here, I'm just using some multi-layer perceptron which is mapping my variables X and Y. Sorry, these are outputs and my inputs is variable P, which is my parameter. So I'm just finding this dependency of my primal decision variables based on parameter. And I have just few lines of code when I define the list of objective constraints. I can select the loss function. You can use penalties, barrier functions, or more advanced methods like augmented Lagrangian that will work on stochastic gradient descent. And then you just train your model like you would do in PyTorch. You are searching for the parameterization of a neural network that fits the problem, satisfying the constraints, and finds the distribution of the optimal problem solutions for a distribution of problems. Yeah, computational graph can be really complex and sparse. I will skip those. These are automatically generated by the tool. And here are very two example problems, non-convex, nonlinear optimization problems in two-dimensional domain. These are test problems in constraint optimization, Rosenberg and Himmelblau problem. The objective is to find the solution which is inside this half donut on the non-convex objective. The green one is like what you obtain with one solution of the IP-opt. The red one are our solutions, which are given by neural networks. So they are not exactly there because in this simple case, I just use penalty methods without much tuning, and it was solved like within half an hour on my laptop. But what is the key benefit of this? We can solve this in milliseconds at large scale with thousands, tens of thousands decision variables compared to solving the IP opt online. So orders of magnitude execution speed up with only one investment in offline optimization. And because I don't have a time, I will skip the molecular dynamics example. I used a lot of time in explaining the methods, but I will be happy to discuss them offline. And maybe pitch the idea of differentiable predictive control, because once we have surrogate model like neural differential equation, can we do control? Where the system model can be given by neural network representing the differential equation. Now we can leverage the same infrastructure we built on constraint optimization to solve optimal control problems by penalizing the optimal control objectives like the deviations from the reference trajectories and constraint penalties for safety. And this is just a hello world example on control theory. How do you stabilize unstable system? You have linear state space model where in open loop will run away to infinity. We have model predictive control objective, which is translated to optimal control problem. And what we do, we formulate this in the Lagrangian form. We take the sensitivities of the optimal control problem to represent our policy gradients. As opposed to black box reinforcement learning, we don't need to learn any value function because we are engineers and we know our objectives, so we can formulate them. If we don't know our model, we do system identification, but the model with parameterized objective function and terminal constraints will give you fully parameterized value function. So that's kind of the insight why I would advise not to use reinforcement learning when you are having engineering applications. Yes?
Have you done anything where you're also online learning
A and B? Yes.
the model?
Yeah, adaptive control. Yeah.
So here you're generating pi though, right?
Yes, here we are learning the control policy given the system dynamics model and desired objectives.
But can you do both at the same time?
Yes, you can do both at the same time because everything is differentiable and whatever is in your computational graph and you have trainable parameters, you can make them available to your optimizer. I would prefer to start with two processes from control theoretic perspective. First, do system identification, then learn policy. After you have policy, then deploy, and you can update both in adaptive fashion. Yeah, so advantage compared to black box, this learns very, very fast. Converges very, very fast with a couple of dozens of epochs. You can solve this on CPU, even on laptop. Like you don't need huge computation power. That's why we want to scale this for power systems where we can leverage the institutional computing for very large optimal control problems. And another advantage is that you can also analyze this problem from control theoretic perspective, like stability analysis. One example, this is my last example slide, is when we have been using this for economic dispatch on simple power network problem. There we don't know the ABCD matrices. We don't know the nonlinear equations, but we know there are differential algebraic equations. We learn the Koopman model, and then we just plug it in the same infrastructure that we used before, learn the control policy to do the economic dispatch. And the basically outcome is like we obtain 5 orders of magnitude speed up compared to interior point online solver in this particular example without losing much of the solution quality. So these are very early explorations and software developments from our team, and we would very much be happy to hear your feedback, suggestions, feature requests, and here I would like to thank you very much for your attention.
Do we have any questions? I know people were asking them as we went along.
Yeah, I just try to understand the KSI in your first part. You say this is the parameter, but to me, it's like it's a data lag. From KSI,
yes,
you use the network for any model to get a map.
Yes.
X related to KSI and the theta. Is this the case? Oh,
Yes,
the
so
parameter.
from machine learning perspective, Xi is a data point. You sample your independent variables, but from constraint optimization perspective, we think of it as a parameter of the constraint optimization problem, because this sample parameter can represent different initial conditions, or doesn't necessarily need to be scalar. It can be vector, it can be tensor. Like
Yes.
can represent the whole right-hand side of your inequality constraints.
But you needed to do a sampling to get those parameters.
Yes.
Right?
Yeah,
Oh,
are you assuming you have your polytopic constraints, or you have some distributions from which you want to sample? So you are definitely exploring certain region of the parametric space that is defined by you when you are defining parametric optimal control problems or parametric constraint problems.
So another question, you have two different constraints in the second part, third part.
Mhm.
So you just simply add upon this total loss function, or you needed to do something to tune that?
Yes, there's an excellent question, and that can be a bottleneck when you have especially many constraints. So there are these terms that are called Lagrange multipliers. In very simple penalty method, you just impose them like hard. You need to do a lot of grid search if you have a lot of constraints, and then like which one is more important, and you need to do some proper variable scaling that is important to have your problem well posed. More advanced method like augmented Lagrangian will find these tuning factors for you. Also in interior point method, like those Lagrange multipliers are computed iteratively with some schemes.
Okay, thank you.
Yeah, thank you very much.
Any more questions? Sorry.
Good talk. So I had a more like a comment. So one of the issues with differential programming is that you sometimes lose the gradients when you're back propagating it.
Yeah.
So are there any tools or like debugging methods that you have that could help identify such situations?
Yeah, excellent question or comment. Well, depends on the problem. Some problems have more well-posed gradients than the others. Of course, like this is the work of the engineer. How do you well-pose the problem? One insight what we have, when we want to learn neural differential equations or neural state space model for dynamical systems, simple thing as spectral properties or spectral constraints on your weight matrices will avoid blowing out your gradients, but then you need to avoid not pushing it too low. So linear algebra can do awesome tricks here. Do just linear factorization of your matrices, bound their singular values in certain range, and like you are good to go in many cases. Like can be very robust and simple way. Yep.
All right, well, thank you very much. We appreciate
Thank you
that.
very
It was
much.
nice to see a Gibson fan.
Yeah.